Your challenge is to meet your customers' high expectations while maximizing your profits. Challenges from your competitors, rising costs of materials and labor, and new market regulations don't give you time to breathe. Errors in your manufacturing process are costing you money, and worse, customers are returning your product. How can you reduce this negative cycle and build confidence in your design and engineering process? How can you reduce the number of errors that are absorbing your company's time so that you can focus on eliminating these errors from your next product line? It's tempting to stick with the way we've always done things. At least you know the risks. Traditionally, digital simulation has been expensive, a third-party service, which is left to the end of the design process simply to document an already proved result. But you could be using technology that you already own to shift the balance. By building your design, engineering, and manufacturing process around a single, three-dimensional digital model, you can coordinate your team's efforts to prevent errors. The simulation of the digital prototype can prevent overbuilding or underbuilding your product, maximizing your potential profit. And updates to the 3D model can be consumed downstream. Your team always has the correct and up-to-date information. Because simulation software is built into your design software, updating the 3D design model automatically updates the simulation study, ready for the new design to be tested again. This allows you to simulate early and often, pulling this feedback into your designs to improve your product's quality. Prototyping and simulating your product digitally gives you the confidence that your design will meet your customers' expectations while minimizing the number of costly physical prototypes. You can build the time into your process to improve your product capabilities using the 3D model you already have and the simulation tools you are already entitled to as part of the Autodesk Product Design and Manufacturing Collection.
Hello and welcome to the video portion of What Can I Simulate? Choosing the Analysis Type. My name is Mike Fiedler. I'm a Designated Support Specialist here at Autodesk. I'm going to walk you through today's presentation. So one of the things that we're going to do is open up an Inventor assembly, and this assembly you can see has quite a few different parts on it, and we can utilize different parts to take a look at different features within the simulation programs. And today I'm just going to start with one of the arms of the assembly here, and I will show you what analysis types are available inside the Inventor environment, and then we'll go ahead and take a look at how to set up a basic analysis. So I've already isolated that arm, and if you wanted to access some simulation from within Inventor, we can go to the Environments tab, and off of Environments I can choose Stress Analysis. And when I choose Stress Analysis and I say Create Study, you can see the Inventor Stress Analysis module here contains two different simulation types here. There's a static stress analysis type and there's a modal analysis type. In addition to those two finite element analysis types, you can also perform some shape generation here. That is to say that you can have the program determine what is critical material given the constraints, given the loads on the geometry, and I'll tell you potentially where you can remove material from the component that you have. We're going to go into the other analysis module or package that's here. If I go to Environments, then we're going to select Autodesk Inventor Nastran. The reason we're going to take a look at Inventor Nastran is because out of the simulation products that are available, currently this one has probably the greatest breadth of analysis types available. So as I come into the environment, you can see that we are set to a linear static, and if you wanted to change the analysis type, we can just double click, and then from the pull down menu where it says type, we can see there are all the different analysis types. So linear static, probably the most common analysis type that you're going to choose. You say I have some constraints, I'm going to apply some statically stable load on it, and I want to know what my deflections and stresses are from that. And then of course you have your normal modes if you need to figure out what sort of natural frequencies the structure would produce or react to. And then you have your buckling module. We have a number of different vibration modules. There's fatigue analysis available within Inventor Nastran. You also have heat transfer module, so if you're going to apply some temperatures and say what does the thermal distribution look like, you can access those modules. And then at the bottom we have explicit dynamics and explicit quasi-static. So quite a few different analysis types, and by this point that you're viewing this video, you should have seen a few prior slides where we discussed in short what these different types of analyses can do. So if need be, you can always scroll back a couple slides and read those short descriptions on them. Let's go ahead and continue on with the setup to see how to do a basic analysis within Inventor Nastran for linear static stress. The first thing is each analysis that you do is going to need some basic components to that, and that's generally the material. You need to have some sort of constraints, you need to have some sort of loads, you need to have a mesh. And once you have those fundamental elements to it, then you can perform the analysis. So we can see that this particular component already has a material associated with it. It's a mild steel. If I wanted to change it, I can right click there and say edit, and I could type in values here in the fields appropriate to my material, or I could say select material, and then I could utilize the material library, either the Autodesk material library, the Inventor material library, or if I say load database, I can use the Nastran material library as well. So multiple different ways to get different sources of materials. I'm going to go ahead and say select material. We'll utilize something out of the Autodesk material library, and let's say that we change it to we'll scroll down a little bit further here. How about a steel ASTM, and let's take the A36. Okay, so you can see it reads in the values, and we'll just say okay. So now if I go back to the menu tree here, I can see that it has assigned the new material. So after the material, again, you need to have some sort of constraints, you need to have loads, and the mesh. So for the constraints, this end of the model is where the bucket was, and then the attachment points to the rest of the assembly were via these two holes here. So I'm going to apply my constraints here. And in this particular case, I'm just going to say that I need a constraint, and I'm going to change from a structural to a pin constraint, zoom in, select the surface that I want, and fix radial and axial directions and say OK. Now in a future module or a different module, we will talk more about loads and constraints. For the moment, we're just going to explore the basics of setting up an analysis so you can see what we'll say the minimum requirements are in order to perform an analysis. So let me go ahead and select pin constraint. Select that surface. Again, I'm going to fix radial and axial. Say OK. So now that I have some minimum constraints to keep the model statically stable, the next thing I can do is apply some load. So I'm going to tell it that I want to apply a load, select the surface, and then given that surface and the geometry that I have, let's rotate the model around a little bit. We're going to put it in the -y direction. So I'm going to say -10,000. And you can see here we're in metric, so this is magnitude of newtons. We'll say OK. Alright, so at that point, I think the next thing that we can do is generate our mesh. So I can go into mesh settings. I can say generate mesh. That applies the mesh on the geometry, and then I can determine if that mesh is suitable or whether I want to go finer. Again, we'll have another module if you're interested in learning more about meshing and all the different controls that you have with meshing, so make sure to check that one out. For the time being, I'm just going to go ahead and reduce this mesh size maybe about half. And I'll say generate mesh. And there we go. There's our new finer mesh on it, and that looks reasonable to me. So now we have basically the minimum requirements, right? We have the material associated to it. We have our constraints, the two different pin constraints that I added. And if you ever need to edit anything, you can just double click and get in and edit the constraints. I have my load. I can double click if I need to edit it. At that point, we're ready to run the simulation. So I'll just go ahead and say run. Pretty fast simulation. It's already complete. And then of course I'm in the results environment, and we can take a look at what the results of our analysis are. So by default it's going to show me the stresses, again in terms of a metric unit system, so that's megapascals. The minimum is about 0, and my maximum in this case is about 14, we'll say 15 megapascals. If I wanted to look at it in a different unit system, say the English unit system, I can go to the pull down menu and select PSI, so I can see what that is. Maybe I need to capture some snapshots for somebody who wants to see it in English inch units. As I go to the pull down menu here, I can take a look and see what our displacements are. And again, we're in terms of millimeters here. It's about 0.34 millimeters, which equates to roughly 0.0134 inches. So that is a little bit of an introduction to what different analysis types are available within the Inventor environment, both within the Inventor simulation and Inventor Nastran. Let's talk a little bit about changing it up. So kind of related to linear static stress perhaps is the nonlinear static, right? So if you have a material which is nonlinear in nature, or if you expect it to have rather large displacements, you might need to utilize a nonlinear static analysis. And I'll go ahead and show you how to set up one of those analysis too. So what I'm going to do is right click on my analysis here, and I'm just going to say duplicate. So this copies it into a new analysis. I'm going to rename this. We'll call it analysis 2 nonlinear. Alright, and then again, to get into where the analysis type is, I just double click, and I'm going to go to the drop down menu, and at this point I can change it to a nonlinear static. Now for this particular analysis, given those loads that I just added to it, those constraints that I just added to it, you saw the results, right? So the results were relatively low stress and really small displacement. So there isn't necessarily particularly any reason that I have to go into a nonlinear static analysis for this. Just wanted to show you perhaps the differences between linear and nonlinear, and probably more so the similarities. One of the differences here is when I switch to a nonlinear static, we see that we have the large displacements. So it will account for large displacements and whether those loads are following the displaced geometry or stay in their initial orientation. So that's one of the advantages of nonlinear analysis. And then one of the other things is in the material. So when I go into the material, here in the material, what I can do is go down to the nonlinear button. So the other half of nonlinear analysis beyond just having large displacements would be the nonlinear materials, right? So I can go in and access nonlinear, and there I can tell it whether it's a nonlinear elastic. So I can define stress strain data points for my curve. I can go into an elastoplastic, and that would be like a bilinear curve. So you can see that we can define the tangent modulus past the yield stress, and so there are the fields where I can input these values, the initial yield stress, so it knows when that occurs, and then it needs to know what slope to follow once we pass the yield, and that would be defined by the tangent modulus, which can be input right there. So you could certainly do that as well. Maybe we'll do that. All right. So having chosen that material model, now you can see it says that the nonlinear material is on. So that way, if we were to apply a load and we exceed the yield, now it knows that it needs to start following the slope defined by that tangent modulus. At that point I can go ahead and say OK. The other major change with switching to a nonlinear static analysis is that then you have to have some sort of nonlinear setup input. So on nonlinear setup, when I come in here I can define how many increments I want to have the analysis solve within. So in linear static stress, how it basically solves one analysis, it sets up the stiffness matrix and then figures out what our displacements and our strains and our stresses are. The nonlinear analysis is going to break this up into smaller steps. It's basically going to take your load, divide it up by X number of increments, and then come to a final solution whenever we sum up all those increments, if you will. So you can define what the number of increments are here, or if you leave that blank, you're basically telling the program that you would like to determine what you need. So I'm going to go ahead and just hit run. And there you can see that it's beginning to calculate through those different increments. And very shortly, there we go. The solution is completed. So there's my nonlinear analysis results. And again, because we were below the yield of the material, we can see that our stress has not changed significantly. And if we take a look at what our displacements are, we get the same displacement output, right? So you would only expect to see a difference in this if, with the linear analysis, the loads that we had applied would cause it to exceed the yield. In a linear static analysis, it would continue to follow the slope defined by the modulus of elasticity, whereas in the nonlinear analysis, once it reached that yield stress, then it would follow the new slope. But in this case, the loads that we had applied in both cases were below the yield of the material, so our results do not change significantly. Okay. Thank you for watching this video, and we'll see you in another one. Thank you. Hello and welcome to Finite Element Analysis Contact, and today we are going to take a quick look at the contact types. My name is Mike Fiedler. I'm a designated support specialist with Autodesk, and what we are going to do is move over to Inventor Nastran, and we'll take a look at a simple assembly and explore some of the different types of contact. So let's go ahead and do that now. Here we are inside of Inventor Nastran, and I have a simple assembly. As I mentioned, this trailer hitch assembly will be uploaded so that you can access it. And I've imported the geometry already, or opened the geometry in the Nastran workspace, and you can see that we have a couple different parts. We have the ball, we have the hitch itself, we have the receiver, and then we have a pin. And I've meshed it coarsely just so we can run the analysis rather quickly, and I've added the contact into the assembly. So because it is an assembly, we do have to have contact, and currently all the various contacts in this assembly are just set to bonded. We will have a subsequent video where we go over with a different assembly the full start to end analysis, including setting up some type of contact. But if I right click and I say edit, you can see that right now all the various contacts between the parts in this assembly are currently set to bonded, and we'll say OK to that. And let's just go ahead and run that real quick. I should mention, as far as loads and constraints, we have the back face of the receiver fixed, and then I have a load on the ball. And again, everything is currently set to bonded. So you can see that that runs relatively quick. And if we take a look at the model in our results, so we can kind of see from the results of this assembly that it is a bonded type of analysis. So again, we have this end completely fixed, but the receiver is bonded to the pin, and likewise the receiver is bonded to the hitch itself, and also the hitch to the pin, so on. So part to part to part along down this chain, we have all the parts bonded, which means that they cannot pull apart and they cannot pass through one another. There's no sliding allowed. So, you know, given the load that we have on this, we get a bit of a hinging effect here, and we see the max stress occurring here on the hitch itself, where the geometry changes direction here, kind of a radius. So that is the result that we see with this entirely bonded, right? And you may have noticed whenever the solution began to proceed, and maybe I'll jump into the output here real quick. As we go through that, because we have defined some sort of contact to it, we have contact segments. So the program does need to add contact segments for each one of those surface interactions that it sees, even though they are bonded, meaning they're not allowed to slide, or again, they can't pull apart, can't pass through one another. The program still needs to have contact segments in order to track the interface between those mating surfaces. So that does add to the solution time. So when we start to set up our analysis, or even when we review the results of our first analysis, we might ask ourselves, is this really what's going on with the model, and should I change it? In this particular case, maybe we decide that we do want to change it. So let's consider what's going on. So for instance, the ball here is threaded into the hitch, and if I rotate it around, you can see that there's a nut there. So maybe that one's okay to consider as a bonded type of connection. But really, the hitch slides into the receiver, right? And then it's just the pin going through here that keeps the connection between the receiver and the hitch. And then likewise, the pin is generally slid in, and then there's like a cotter pin or something similar to maintain the pin through that hole. So in that case, we might say to ourselves that the bonded connection is not appropriate. So as far as changing them, I'm going to change all of them except for the one surface contact that is the hitch ball. I'm going to go ahead and leave that as bonded, and I'll just shift select all the other contacts, and we're going to change those to a different type of contact. So let's go to Edit, and from the pull down menu there are all the different types of contacts. So separation is the fully general. It's allowed to slide, it's allowed to pull apart, it just prevents parts from passing through one another. And then we have the contact type that we just used, the bonded, which is the same as a fully fixed surfaces between adjacent parts. And then you have kind of the specialty version of the separation. There's the sliding no separation, so it's just allowing sliding contact, but again, it will not allow the parts to separate. And then the inverse of that says I'm going to allow separation, but I don't want to see the parts sliding. Underneath that, you have your offset bonded. So this is generally utilized in the case where you have gaps between parts. Generally arises in a weldment. So when people have a 3D CAD assembly, and maybe there's gaps between the parts because in the final product we're going to weld between those different parts. So in those cases, you can use an offset bonded in conjunction with specifying your max activation distance to account for the gaps between the parts. And then you have different shrink fit options whenever there are interference and you're trying to solve for what those interferences are between the parts, see what the stresses are and the displacements as a result of that. We're going to go ahead and make it fully general, so I'm going to set it to separation, and we'll say OK. And when I do that, you notice that the symbol over here in the menu tree is a little bit different than what the bonded one is, just to let me know that there's some difference in my setup here. And at that point, we can just go ahead and run the simulation again. So this one's going to take a little bit longer. I still have the same number of contacts that it'll do between the same number of contact segments between the parts. But because the program is going to allow for the ability for it to slide or for parts to pull apart, it needs to get into an iterative process in order to determine, is it trying to slide, in which case to allow that, if they're trying to penetrate, to prevent that, and of course, if they're going to pull apart, it has to allow that as well. So it does become an iterative solution, and you can see in the output that it was going through the iterations right then. And of course, overall, that analysis takes a little bit longer. And from that, as a result of changing up the contacts, perhaps some fashion that is more representative of what the real-world geometry will do, we can see that we have even impacted the location of the max stress. So we still have stresses in this region, but it's no longer the location of our max stress. And our max stress now occurs in the pin region, where the pin comes into contact with the hitch. So again, being that we're fixed back here on the receiver and we're loading up the hitch ball is bonded to the hitch, so the hitch is going to want to slide forward a little bit, as it slides forward, it makes contact with the pin, and so the pin then comes into contact with the receiver on one side. So we can see that it's loading up and we're getting some stress on that side. And you can see if we zoom in here, because it is separation contact, it allows the pin to pull away from the receiver here. So we're even seeing a gap there. So this is probably a little more representative of what will actually happen with the real world condition. So that's why we have all the different types of contact there, so that we can set up our model appropriately, and it will have an impact on your results in most cases. So just be aware of that. I'm going to leave you with one final note. I did mesh this rather coarsely. I believe I meshed this model at either 1/4 of an inch or 1/2 an inch, so that we can solve it in real time rather quickly. But if you do end up downloading this model and you run a finer mesh on it, you should still see the separation here. Presuming that you use separation contact, you should still see stresses develop on this side, but the maximum stress will actually occur in the radius here, where the hitches build up around the ball. So we have meshed the model so coarsely in this particular case that we haven't captured that detail. So that's another good point to make sure that your model's always adequately meshed. So hopefully that helps to provide a little bit of information. And again, in the upcoming video, we will go through more detail on the entire setup process of an assembly start to finish. Okay, thank you.